Hi everyone. In the last video, we solved this system and we got these three ordered pairs forming our solution set. Now, if we think of these ordered pairs as their corresponding points in the xy plane, the Cartesian plane, what do these points have to do with these two equations? In particular, the graphs of these two equations. Well, remember the basic principle of graphing. The graph of an equation consists of all points whose coordinates do what? Satisfy or solve the equation. Whose coordinates satisfy or solve the equation. The graph of an equation consists of all points whose coordinates satisfy or solve the equation. That's true in Cartesian coordinates, polar coordinates, 3D coordinates. That's a powerful concept, the basic principle of graphing. So the graph of 3x plus y equals 2 consists of all points whose coordinates satisfy or solve this equation. The graph of this second equation consists of all points whose coordinates satisfy the second equation. How do you graph these, by the way? How do you graph 3x plus y equals 2? I'll give you a hint. Put this in slope-intercept form. Subtract 3x from both sides. Y equals negative 3x plus 2. What is that? The graph of this is going to be a line, which you can graph either by using the slope-intercept form or by finding the two intercepts, right? The x-intercept and the y-intercept, and you can graph the line. Let's have Desmos do it. Desmos, let's graph 3x plus y equals 2. So again, either by using the intercepts at 2/3, 0. Notice that solves this, 2/3, 0. And also, hey, 0, 2. Sound familiar? 0, 2. That's another intercept for this line. It's the y-intercept. Okay. Based on these two intercepts, we can graph the line. Or you can use the slope-intercept form, right? That was y equals negative 3x plus 2. It's the same line, right? We use the fact that the y-intercept, again, is at 0, 2, because b is 2, and the slope is negative 3. If you run 1, you go down 3. But either way, we can get the graph of this equation. It's a line sloping downward, and whose y-intercept is at 0, 2. Remember him. Now, what about the graph of the second equation? Well, remember, we already solved that for y in terms of x. That was star. Remember the star relationship here, right? It was y equals 2 minus x cubed, because we like to have y as a function of x. Y equals 2 minus x cubed. Let's rewrite this as y equals 2 minus x cubed. Y equals 2 minus x cubed. All right, over here, let's keep this a secret. Y equals 2 minus x cubed. All right, so let's try to figure this out. What does this graph look like? First of all, what does the graph of y equals x cubed look like? What does the graph of y equals x cubed look like? That's going to be a rising snake going through the origin, right? It's odd. What if we have y equals the opposite of x cubed? What happens if I put a minus sign in front? Flips it. What happens if I add 2 to the right-hand side? What's going to happen? Raises this by 2 units. And look at this. Instead of going through the origin, this point now goes through, hey, 0, 2. This is an intersection point between the two graphs. So if you remembered your graphing from chapters 0 and 1, you should be able to figure out that 0, 2 is a common point. It's an intersection point, and therefore it's going to be one of the 3 solutions we have here. Oh, and how do we know we have 3 solutions? Let's zoom out. If you do a decent job of graphing, you should be able to see that we're going to get 3 intersection points. In addition to the intersection point at 0, 2, we're going to get another intersection point somewhere in quadrant 2. That's a decimal approximation. Now, I realize that you may have a hard time figuring out that that quadrant 2 solution is going to have these coordinates. I doubt any human being could look at this point and go, oh, well, this is negative root 3 comma 2 minus 3 root 3, or is it 2 plus 3 root 3? I don't think any human being can go, oh, this is going to be 2 plus 3 root 3. Although actually, negative root 3, I think some students will recognize this as being close to negative root 3. So some observant math students might observe that this is about negative root 3. So I can give you the negative root 3, but the 2 plus 3 root 3, can any human being look at this and go, oh, hey, 2 plus 3 root 3? No. And by the way, you might only get the negative root 3 because you see this number here. If I just said, hey, look at this point here, right, without the corresponding coordinates, you just know it's some point in quadrant 2. You can try to estimate it, but not to this level of accuracy. Likewise, it appears that we're also going to get an intersection point in quadrant 4, and it turns out to be this point over here, this quadrant 4 point over here. But again, I can't imagine any human being just looking at this and going, oh, that's going to be root 3 comma 2 negative 3 root 3. I can't imagine any human being identifying that point. Desmos can approximate it. Notice that's about positive root 3 there. And if you do a decent job graphing, then you might even be able to estimate the coordinates. But 0, 2, you should have right on, 0, 2. And at the very least, you should know that you get 2 additional intersection points, one in quadrant 2 and one in quadrant 4. But in order to find their exact coordinates, then of course, it helped to solve the system algebraically, mechanically. Now let's review this graphical method. Oh, and by the way, as a check, this is a check to see that there are in fact 3 real solutions. There are 3 intersection points. Okay, the graphical method. So the graphical method, which you may remember from your old algebra class, this method for solving a system of equations requires that we graph all the equations and then find the resulting intersection points. This is the key principle. There is a relationship between the real solutions of a system and the intersection points between the corresponding graphs. Okay. These points correspond to the real solutions of the system. We're not dealing with I. We're going to keep it real in this chapter. In fact, we're basically going to keep it real throughout the final material. Now, books neglect to mention that this method is highly unreliable because back in your algebra class, your book was used to giving you systems with integer coordinates in solutions. Now here, yes, 0, 2, that's one that we can pick up exactly very nicely. But your old school algebra books were less likely to get solutions like these because they were too clean. See, I'm being more mean to you. I might give you a system where you get kind of weird looking coordinates like those, right? That's now fair. All right. So you can't just assume that the coordinates will always be integer. Here they are, but for these guys, they won't be integer or even rational. Okay. And in fact, even if you eyeball something, even 0, 2, some students might ask, why can't it be something like this? So although many textbook problems are designed to have nice solutions, we can't always assume that our solutions will only consist of integer coordinates. It's quite possible that your solutions might be uglier, like irrational. And sometimes when you graph, maybe 0, 2 isn't the solution. Maybe it's just a nearby point, like that. Although, if you really think about it, in our example, you should be able to figure out it's exactly 0, 2. So again, I had an old version of Mathematica sketch graphs for these 2 equations. And like I said, even with a decent graph, you should be able to figure out that there are 3 intersection points. One is at 0, 2. You should be able to get that one exactly. You have one other solution in quadrant 2 and one other solution in quadrant 4. So 3 real solutions corresponding to 3 ordered pairs. In terms of getting the exact coordinates for these guys, you better work out the mechanics, as we did before. Now, in general, I wouldn't recommend the graphing solution as an overall approach Because again, how in the world are you going to pick up a solution like that and a solution like that? Granted, you could pick up this solution, but how are you going to pick up these two solutions? So I wouldn't recommend the graphing approach in general. However, there are some cases where it can really help, aside from just picking up a point like that. Okay, let's consider this example. And if you do a decent job of graphing, so be reasonably careful, reasonably accurate, then you should be able to figure this one out, just graphically. Find all real solutions of the system, 1/2 y equals 1/2 x plus 1, and x squared plus y squared equals 1. First of all, a lesson. A legal move, a legal operation that you can perform on a single equation, you can perform to that equation even if it's in the context of a system. So look over here. 1/2 y equals 1/2 x plus 1. What are you just dying to do to both sides of that equation? Why don't we multiply both sides by 2? I'll do this in blue. Let's multiply both sides by 2, because I know you're itching to get rid of that fraction. Okay, we can do that. Remember, the 2 distributes through, all right? So then when we do that, okay, we then get y equals x plus 2. Don't forget the 1 here becomes a 2 here, because we're multiplying, we're distributing in the 2. Again, I'm making the point that operations that are fair for a single equation are also fair for a single equation in a system. Now, let's consider graphing these. How do you graph y equals x plus 2? How do you graph y equals x plus 2? Well, that's going to be a line. Slope 1, y-intercept at 0, 2. Once again. But now, how do you graph x squared plus y squared equals 1? Do you remember section 0.13? That is going to be a circle. The classic unit circle centered at the origin. Okay. Now, if you point to your screen, maybe you can even draw it on your screen. Draw for me that unit circle. Don't be too sloppy. Don't be too sloppy. X squared plus y squared equals 1. Let's make it a different color. Yeah. How about purple? All right. So if you do a decent job of graphing this circle, don't go nuts and make it too ovally. Don't make it an ellipse, all right? If you do a decent job of graphing this circle, how many intersection points do we have between this circle and this line? None. If you do a decent job graphing these things, the answer is none. So therefore, what's the solution set? For the first time, we see that the solution set will be the empty set. There are no real solutions. There will be no pair of real values, x comma y, that will satisfy or solve the first equation and satisfy or solve the second equation. Not going to happen. Empty set. There are no real solutions to the system. The solution set is the empty or null set. Now you might ask, well, let's say I don't trust my graphing. I don't blame you. You've seen my circles. You've seen my circles. So how do you do this mechanically? Well, look at this. This is really set up for the substitution method. I already have y set up in terms of x. Let's substitute into the other equation. But now you're going to have to work out the square of x plus 2. And take a minute, folks. When you perform the substitution, you put x plus 2 in for y. What is the square of x plus 2? I'll give you a moment to remember this. This is Chapter 0 review. Let's work it. We have y already expressed as a function of x. Let's substitute this in. And we get, okay, x squared plus, what's the square of x plus 2? It's x squared plus, please do not forget this. I'm going to put this in red. A lot of students forget this. Don't forget to take twice the product of the two terms, the 2ab term. Okay, remember that square of a plus b, remember that meme I showed you with the teacher, the mad teacher? The square of a plus b is a squared plus what? 2ab plus b squared. Don't miss the middle. Don't miss the middle. Twice the product of the two terms. 2 times x times 2. 2 times x times 2 is 4x. You need the 4x. I don't mind taking forever to push the 4x because so many students forget it on the homework. I see that. Okay, don't miss that middle term. Plus, the square of 2 is 4. People get that. Equals 1. What's x squared plus x squared? It's 2x squared. Now, this has an x squared term and an x term in it. I'm going to want to isolate 0 on the right. Whether I'm preparing myself for factoring or the QF, the quadratic formula, I want to isolate 0 on the left. Subtract 1 from both sides. 2x squared plus 4x plus 3 equals 0. If you try to factor this old school, you're out of luck. There are no rational zeros to this left-hand side. There are no rational solutions to this equation. So let's try the quadratic formula. All right. And what happens when we try the quadratic formula? Well, right off the bat, you might have wanted to work out the discriminant, b squared minus 4ac. This is the discriminant. That's the discriminant, b squared minus 4ac. I'll put the square here. If you work out b squared minus 4ac for that left-hand side, a is 2, b is 4, c is 3. The discriminant, b squared minus 4ac, I'll put this in blue. The discriminant, b squared minus 4ac, turns out to be negative 8. So even without plugging into the other parts of the quadratic formula, if you have a negative discriminant, then you're dead as far as real solutions go, because you're going to have an I involved in there, inevitably. So just by taking this and finding the discriminant, once you find that this discriminant, b squared minus 4ac, once you find the radicand there is negative, you realize game over. What's the solution set? It's going to be empty. Because you can't even find real solutions for just x alone, let alone an ordered pair. You need real solutions for x if you're going to have real solutions as ordered pairs. Solution set is the empty set. You're dead right here. There are no viable real values for x, so the system has no real solutions, and the solution set is the empty set. And this confirms our findings for method 1. There are no intersection points between the circle and the line. Ugh, horrible. All right. Again, once you find the discriminant's negative, you know there are no solutions. All right. And by the way, a system with no real solutions, if the solution set is empty, that's often called an inconsistent system in the sense that the two equations are not reconcilable. Actually, the original system was up here. Okay, we say that the system is inconsistent because it has no real solutions. There is no ordered pair solution, x comma y, that would be consistent as a solution to both the equations. Inconsistent. They don't go together to give us a solution. All right, next up, we're going to discuss the addition or elimination method next time.